Hi, I'm Dr. Courtney with the Quantitative Reasoning Center. It was the famous Italian scientist Galileo who said, "The laws of nature are written in the language of mathematics." So the laws of nature are very important in keeping airplanes in the air and putting ordnance on target. So to master these laws of nature and to have our best advantage in armed conflict, it's very important that we master the language of mathematics. So today we're having a look at 14.3, problem number 71. We're asked us to show or prove or verify that if we have a function u is equal to e to the negative alpha squared k squared t times sine of kx, that solves this differential equation. And so we got to break this down. First we want to think about what's the big idea. The big idea, or to identify it, is we just want to use the really the definition of partial derivatives to show that u, which is a function of t and x, because t and x are the variables and the k and the alpha are just parameters that appear in the function, to show that u of t and x satisfies the differential equation. Or, well, how do we develop this? Well, this is one of those situations where it's kind of prohibitively difficult to draw any kind of picture that would make sense. I guess if we just assigned alpha equals 1 and k equals 1, we could graph it because it's a surface and the variables k and t. But we really don't need to go down that road, so let's go ahead and make our plan. So the first thing I would do is I'd write the differential equation using the partial x and the partial t operators, because a lot of times it's easier for us to understand what's happening if we use the operators in this form rather than the subscripts to denote partial derivatives. Alright, so we'll do that, and then we'll compute partial u, partial t, because that's what's going on here, partial u, partial x, not because this appears in the equation, but because computing the first partial derivative with respect to x is a necessary intermediate step to computing the second partial derivative with respect to x. So we compute the partial derivatives, substitute into the equation, and this is our differential equation, and then kind of inspect, possibly simplify, and verify that starting with this function, computing the partial derivatives, plugging back in, that the differential equation is going to be true. Alright, so what does this notation mean once we switch it to the operator notation? It means partial u, partial t is equal to alpha squared times the second derivative of u with respect to x. Alright, so that's the first step in our plan. And now u is this business here, so let's go ahead and rewrite this for convenience. It's e the minus alpha squared k squared t times the sine of kx. So partial u, partial t, and sometimes it can be useful to sort of just identify where the variable is because there's lots of letters running around. So the derivative of e to the stuff is still e to the stuff, but by the chain rule, you end up with a factor of that stuff coming out in front. And since the sine kx doesn't contain a t, it just kind of comes along for the ride. So this would be negative alpha squared k squared e to the minus alpha squared k squared t, and then times, well, we make it an asterisk so it's clear that we're not multiplying by x, times sine of kx. And we can actually simplify this because all this stuff is still the same as u, and all we did was balance out in front a negative alpha squared k squared and then another factor of the function u. Alright, now partial u, partial x. Well, there's no x in here, so this stuff just carries along. So all this stuff is negative. Oops, take a little care. What we're doing is we're taking the partial derivative with respect to x. There's no x at all in this, so we just carry down the e to the minus alpha squared k squared t. Now the derivative of sine is cosine, but by the chain rule, a factor of this parameter k pops out, so let's use parentheses so we know that the kx is the argument of the cosine function and the k is the extra bit that popped out. And then the derivative of the second derivative is just the next derivative of this. Once again, this just carries down. The derivative of cosine is negative sine. And then we have another factor of k popping out, so we can just square the k. So we can simplify this, because again we notice if we take out a negative k squared, then all this other stuff, the sine kx and the e to the stuff, that's just u. So the second derivative of u with respect to x squared, or with respect to x, the second derivative, is negative k squared u. So now we can go ahead and plug this back into our original differential equation. And we see that the partial derivative with respect to t is minus alpha squared k squared u. So we're asking the question, because this is what we're trying to show, is this equal to alpha squared times the second derivative with respect to x? So we have a minus k squared u. So if we just bring the minus sign out in front, we have minus alpha squared k squared u. And is that equal to minus alpha squared k squared u? And we can see that they are exactly equal. Alright, so let's revisit our idea format. First we identified that we just wanted to compute the partial derivatives and plug in. Our plan was to do that step by step. And this was the execute or evaluate phase of the idea problem solving format. And now we're left with the assess step. Well, when you're asked to prove something and you go through it sequentially, carefully show all your work, and you end up with the result that shows an equality of the thing that you were asked to prove, you feel pretty good that you verified that the function given is indeed a solution to the differential equation.